Today's lecture, we are going to discuss about the partition coefficient. So, what is actually partition coefficient? We can think it as uh, a substance which is soluble in, let's say, different solvents. So, let's say two of the solvents are like which where this ammonia is soluble. One of them is aqueous or water. Another is any of the organic, let's say, organic solvent. It will be any specific solvent where this substance is soluble. So let's say, for example, ammonia dissolves in one of the organic solvent. Organic solvents are, let's say, ethanol, methanol, or other sort of solvents. And it also dissolves, ammonia also dissolves in water. So when, let's say, we place, obviously, most of us have seen if in water, let's say this is water, on top of it, let's say we pour oil, then what do we see? We see two layers, like they separate each other because they have like difference in like their density. So we can see the difference. This has nothing to do with that, but like for the visual effect, if we try to consider, let's say instead of now this oil, we have taken a vessel, we placed, let's say water. Now we have given here ammonia. Now ammonia dissolves here. After some time, let's say we place some organic substance, this organic substance over here, which does not have like anything, just pure organic substance. Now this organic substance, when let's say we shake or we like do not shake even, like when we try to mix it, some of the ammonia which is dissolved in this like water, those which are in aqueous state, they will turn or try to get dissolved in the organic substance. So they're being moved or they're moving from this aqueous state to the like organic state or dissolved in organic state. While some are in organic state, they will try to move backwards to get dissolved in the aqueous state. So this cycle continues, and the constant which sets or the ratio, let's say there is a rate at which the aqueous state transfers or converts to the organic state. Let it be x. And there is another rate which converts the organic state into the aqueous state. Let's say this rate is y. So the ratio between them is known as actually the partition coefficient. So rate x over rate y, that's known as the partition coefficient, and we represent it as KPC. And usually on the numerator, usually, I'm not saying it's the general fact, but usually we place the concentration of the organic value on the numerator divided by the concentration of aqueous ammonia. So that's basically our KPC. Let's do an example. We are given that in a beaker, 100 cm cube of 100 cm cube of ammonia has been taken, which has a concentration of 0.1 mole per dm cube. In another vessel, there is 50 cm cube of organic solvent. Now, in a in this vessel, they are mixed with each other and and they're mixed with each other and set for some time so that an equilibrium establishes, so that their like solubility, the portion which should be dissolved, the amount which is going to be dissolved in the organic part and the amount which will be dissolved in the aqueous part, in order to set the equilibrium, like some time has been given. Now after the equilibrium has been established, it is found or it is taken, the sample from here is taken into, or this whole system is taken into, uh, let's say into a titration system, titration process, and over there 20 cm cube of it was found that 20 cm cube of ammonia was titrated with HCl. So that means 20 cm cube of ammonia was being titrated from here, from this overall solution into HCl. So a 20 cm cube of sample, we can say a 20 cm cube of like sample was being taken and it was titrated with the HCl. Now HCl was taken in the burette. Now initially the burette has, let's say, the starting point is at 0. As it decreases, the end point of HCl was mentioned as 9.4 cm. That means the total amount of HCl being used was 9.4 cm. Now if we try to focus on the concept, this is a base, isn't it? Ammonia is a base and HCl is acid. But when is ammonia a base? It is base when it is dissolved in water, not in other solvents. So that means only the aqueous portion is going to react with HCl. So that means by doing the calculation, we can actually find the amount of ammonia which reacted from the actual from the aqueous portion. So that means we can find the aqueous portion of the ammonia, and we already know the total. Like we can find from here the total amount of ammonia, and if we subtracted them, we can get the amount which will be in the organic solvent. So let's do the calculation. At first, let's write the equation, which is between ammonia aqueous plus HCl, which should give us a product of ammonium chloride. Okay, so NH4Cl aqueous yeah. So basically that is the part. Now the as they have mentioned, 20 cm cube of this ammonia reacted with 9.4 cm cube of HCl. Let's say the concentration of HCl is given as 0.2 mole per dm cube. It has been given in the question. So now our part is to find what is the actual number of moles over here. We have taken the sample of 20 cm cube, but what is the number of moles actually here? That will help us to do the other calculation. So in order to do that, we don't have much information for ammonia, but we have a relative information, which is the information for HCl. Now we can use it to find the value for ammonia HCl by doing molar ratio. So finding the concentration, the concentration has been given, volume has been given. We can use the concentration formula and find the mole of HCl, which we would get as 1.88 into 10 to the power negative 3, which is actually mole over volume into 1000. So mole, we concentration equals to mole over volume into 1000. Subjecting mole will give us concentration into volume divided by 1000, where concentration is 0.2 times volume is 9.4 divided by 1000. This is going to be the number of moles. Now if we do the simple molar ratio between them, what should we get? That is 1:1 molar ratio. That means ammonia is also having a mole, the portion of ammonia which reacted had a mole of 1.88 into 10 to the power negative 3. Now see in the question, we have been given the total, the other information for the whole of ammonia. From there we can find the mole the actual ammonia was what? Total mole, or total actually. Total was mole equals to, the concentration was 0.1, the volume was given 100 divided by 1000 using the same formula for concentration. So concentration into volume divided by 1000, we should get 0.01 mole. Now we can also convert it to in decimal format 0.00188. Now subtracting them, we would get what? The mole in organic, isn't it? So mole in organic should be a value of 0. Wait. Yeah. So this should be value of, oh sorry, I made a mistake here, which was we, oh no, yeah, perfect. So we did it with correct. Now the portion over here is, so basically what I was saying, that let's say we have to find the portion in the organic, isn't it? We, as I've said, we can simply subtract them, but do we actually get the value by subtracting them? Wisely think, here we have the value for 20 cm cube, but here we have the ammonia for the 100 cm cube. That means if this is the mole for this 20 cm cube of ammonia, then what should be the mole for ammonia in 100 cm cube, isn't it? We need to find that. Like, think it again. We made ammonia reacted with HCl. How much of the ammonia was used? 20 cm cube of ammonia was taken as a sample, isn't it? That means more 80 cm cube of ammonia we didn't consider. So you also need to find actual portion. So if 20 cm cube of ammonia contains 0.0018 mole of ammonia, that means 100 cm cube of ammonia should contain what? Using the unitary method, we can find. So 100 cm cube of ammonia is going to have 100 divided by 20 into 0.0018. This should give us a value of 9.4 times 10 to the power negative 3, or 0.0094. Now we can do the subtraction. Subtracting them, we would get 0.00064 mole. So we have the mole for the organic term, we have the mole for the aqueous term. Now we just need to find the concentration. Now, one thing you can see, at first, like, okay, ammonia for aqueous. Now, in order to find that, we need to do what? Concentration mole. For concentration, we need to do mole by volume into 1,000. Oftentimes, I used to say, if let's say two solutions have been added, we take the total volume, isn't it? But total volume, let's say 10 cm cube and 10 cm cube of two solutions were added, they made to react with each other, and we need to find the now the, let's say, the remaining moles concentration. Then what do? We usually add the volume and get the total volume, isn't it? But in that case, both the solvent were what? Water. But here, both the solvents are not the same. One is aqueous, another is what? Organic. So that means the solvents are not mixing with each other. The solvents are not soluble in each other. Let's say, what I mean is, like, aqueous or water is not soluble in the organic solvent. Organic solvent is not, like, they're not miscible. They don't mix with each other. Like, they don't, like, dissolve in each other. That means we have to find the concentration based on the portion of the volume which are in each of the, like, solvent. So for water, the volume is remaining 100, and for organic, the volume is 50. So doing the calculation, or good, and yeah, so doing the calculation, uh, both the case will use the same values. I mean, sorry, same formula. Over here the volume should be 100, over here the volume should be 50, and the mole over here should be 0.0018, sorry, 0.0094, and over here the mole should be 0.0006. Or 06, yeah, 0.006 only. So sorry, this should be 0.0066, yeah. So the 0.00066, yeah. So that's our number of moles. So after finding the concentration, we would get, for the organic, it is actually 1.2 into 10 to the power negative 2, and for the aqueous, it is 9.4 into 10 to the power negative 2. Now, since we have found the concentration, simply we can find the Kpc values for the organic divided by the aqueous. So 9.4 into 10 to the power negative 2 divided by 1.2 into 10 to the power negative 2. That gives us a value of 0. What value of? Sorry, I misplaced the values. Organic should be on top. So 1.2 into 10 to the power negative 2 divided by 9.4 into 10 to the power minus 2. This should be 0.128. So that's our Kpc value. So over here, in this new experiment, since, like, we were, like, separating the first part, like, there were, like, two parts. One was, like, the division of, like, the 20 cm cube of ethoxy into 10 cm cube and 10 cm cube, and separately, while they were, like, reacting with each other, this ethoxy, like this 75 cm cube of 5 gram of B was, like, made to dissolve or made to mix with each of them in batch. or in separate layer. So when first this 10 cm was, let's say, dissolved into this, like when initially the 75 cm of 5 gram of B was initially dissolved into 10 cm of ethoxyethane, this was the concentration for, let's say, the organic part. So organic, let's say, the mass of organic part is like here given as X, or we take the value as X. So the volume was ethoxyethane was 10 cm, so X divided by 10 into 100 is the concentration. And for the, so the aqueous part, 5 minus X for the mass, that means the concentration should be 5 minus X divided by 75 into 1000. Now simply placing it in the equation, Kpc equals to the organic divided by the aqueous, and Kpc value should be same since the substances are like the same substances are being used, like same solvents are being used, the system are same. So ethoxyethane and water is used, that means the uh, ratio is going, Kpc value is going to be same. So simply after placing the values or doing the equation, the calculation, subjecting the X from there, we should get a value of 1.380. Now this is for the first layer, or the X being extracted after, like from the first layer. After this has been extracted, we need to, in the second part, we need to do further like like mixture of 10 cm cube. So further 10 cm cube is going to be added for its substitution, and now a further separation is going to take place. So let the mass of B in EE be now equals to Y. Now the total mass is going to be what? The extracted value, which was like in the first place, which is 1.38, not the actual like the 5 gram, rather this one, the extracted one, because this extracted one is now mixed with this 10 cm cube of ethoxyethane. So from this 1.38 gram, we are getting, let's say, Y mass from the ethoxyethane part, and we are getting B from the aqueous part, let's say 1.38 minus Y, because the total is now 1.38, so 1.8 minus Y. The volume for, like the, for finding the concentration in aqueous, the volume for water is what, 75. So 1.38 minus Y divided by 75 into 1000, and the concentration for double E of the ethoxyethane, that should be Y divided by 10 into 1000. Now finding, like after finding the concentration, same Kpc value is going to be used for same system, like the solvents are same, which is like ethoxyethane and water. So ethoxyethane on the top, where this one is going to be used, and aqueous one, which is this one, going to be used. And from there, the same method is going to be like we follow, and subjecting the Y from here, 1.38 minus Y, and like this was Y. So after like doing the calculation, we should get the Y, we're getting the Y value to be 0.99, 0.99 gram. So that means this is the final portion which has been separated. So if we go to the previous page where the, it says the two organic layers are combined. So that means the layer from this one, where did it go? So that means like the layer from the first portion over here on the, like the first layer, and the layer from the second layer, like both were like, we can say they were combined and made to like, get this one, made to find like the value for the total organic compound which could be extracted, and the final value is like simply this one. The X value is we're getting in the first layer as 1.38, and the second layer as 0.99 gram. So combining them, after like combining these two, we would be getting a total value. Okay, so I think I made a mistake here, which was we're not supposed to take 1.3. Oh yeah, we are not supposed to take 1.3. 1.3 was extracted from like the portion of the, like the portion from the ethoxyethane part, isn't it? Yeah, let me see it for the simplicity's sake. So yeah, 1.36 was been being extracted from the like the ethoxyethane part. So that means the portion left with, let's say, the remaining portion, which is 1 point like 5 minus 1.38, that is what is we are going to like carry forward. This is 3.8.64. So this is we are going to like forward it. I'm really sorry for the mistake. So this is 3.64. So that means we are going to subtract this value of 3.64. So this is 3.64. So that is actually that this value is correct. This is the correct value. I just misplaced the value here. So this is actually 3.68. So like the value which we are going to use is 3.64 actually. So 3.64. I'm sorry for that. So yeah, that's basically it. And after that, since we combine the mixture, that's what they're like saying in the question, like the both the layers are actually combined. That's the word when I thought like how can, what's the mistake there made. So yes, that's basically it. So x and y are going to be added in order to get the actual value. So this should be 1.38 plus 2.0.99. That gives us a value of 2.37. So 2.37 grams. And if we see on the first part of the question, we see this is 2.14 grams. So that means we actually get a greater portion of the mass. We can extract a greater portion of the mass like into ethoxyethane if we separate the layer. So separating the layer, we get a different, like a greater portion. If you like feel any confusion in this question, like, just get like if you like still like feel the confusion, and do it by yourself again. Like I guess you will be able to do it. I'm really sorry for the mistake I made. So yeah, that's basically it. Another similar example could be done. So it's very similar to the previous one. So for the like mistake I made, so I will be like doing it in a different value. So let's say 80 cm cube of compound X is being taken, like aqueous solution of where the X is, let's say 8 gram, and there is like 30 cm cube of ethoxyethane. They both are mixed with each other, and it is found that 3 gram of the organic solvent, which organic compound, which is X, could be extracted from the organic layer, which is actually this ethoxyethane. That means 3 gram could be extracted from this like, total of 8 gram. Okay. Now the experiment was repeated with 15 cm cube of like each layer. Like previously we did it like we divided in equal portion. Over here we are also dividing it in equal portion. Now, from the first part, we need what? We need to find the value of KPC. So KPC could be found simply by calculating the concentration from each of the term. So finding the concentration for the aqueous term and the concentration for the ethoxyethane part. So taking the two values using the simple concentration formula, we can say the KPC value is going to be 1.6. Now using this KPC value, we are going to like do the repeated experiments part where we need to find the extracted organic substance from the organic solvent from this part. So in the first part, they gave 15 cm cube. So in the same process, we need to do let's say the finding the concentration, which is let's say the we extracted from the ethoxyethane a mass of X. So that means the remaining was 8 minus X, which is in the water. So the concentration could be found by X divided by 15 into 1000 from here. And for this one, 8 minus X divided by 80 into 1000. And using the KPC value we found just in the last page, we can see that the X value is going to be 1.846. Then using this value 1.846, we are going to see how much, like this is the portion which has been extracted from the first layer of ethoxyethane. Now the remaining portion of mass in the water is going to be 8 minus 1.846, which is going to be 6.1538. Now taking this, we will be doing the second part, which is adding this to further 15 cm cube of ethoxyethane, doing the same way. But instead now, if this is, let's say the extracted value is y, then the remaining portion in the water is going to be 1.538 minus y. So doing the calculation again, finding the concentration is like the volume remains same here. They divided by, this is divided by 15 and this is divided by 80. These are like into 1000, in 1000, and taking the same KPC value. In this time we will be getting y as 1.42, and if we combine them we will get 3. Like the value for x plus y, we will get 3.27 gram, which actually satisfies that yes, actually taking into layers, it increases the extraction of the organic substance. Now for the ionic equilibrium's last part, we have the solubility product, which is KSP. So KSP is basically, it's very simple to understand. Like the basic term is like, for an insoluble salt, there is some portion of it which is going to get dissolved. So that dissolving part, which actually like forms an equilibrium of like going to the forward direction and backward direction, that's known as the solubility product. Like how much portion of that insoluble salt is going to be dissolved. This is like the dissolving portion is very minor, but there are certain factors which also like determines this like solubility. Because if we increase the temperature, the solubility increases. Why? Because think of salt in the water. Obviously, salt is soluble, like sodium chloride salt is soluble. But let's say we try to dissolve it into a cold water, compare it with dissolving it in hot water. In cold water, we need to like, let's say, constantly keep on stirring, keep on like shaking and mixing it. But in the hot water, if we just place the salt over there, like we don't even need to wait much, it itself dissolves there. So that's one of the factors like defines the like, or it changes the values for KSP. Now we can think this term as like, we can form an equation in terms of like equilibrium constant if we follow that method. So we will be like getting Kc as the product of the products. So product of the products, which is this divided by the reactant. Now once we move this reactant to the left hand side, Kc times the salt of the insoluble salt, that is actually our Ksp, and this will be equivalent to Ksp with the right hand side being Ag plus and Cl minus. So that's basically it. So this is our actual Ksp equation. So if we do an example, let's say the example says a saturated solution. Saturated solution. A saturated means is like the solution is in its highest state of like solubility. The that there can no more particles which will be able to like dissolve. That's the meaning of the saturation level. So saturated solution of, let's say, given MgF2, which is magnesium fluoride, has a solubility product of, let's say, 1.22 into 10 to the negative 3. You see the KSP value usually being very small values, not even like one, less than one. So yeah, so they are asking us. So the, no, sorry, this is not the KSP value. This is actually the solubility. That's actually the concentration that has been given. So solubility, there's a difference between the solubility and the KSP. So solubility is given 1.22 into 10 to the negative 3, and you usually see it is given as like mole per dmq, which will say that this is actually the concentration, and you will be asked to find the value for KSP in this case. If you write the simple equation mgf2, we will get mg2 plus 2f minus. Now the unit for KSP usually changes. Okay, so KSP value unit, it doesn't remain same. Let's say in the previous case over here, if this is the concentration, like mole per dmg and mole per dmg, in together we would get a combination of mole square 10 to the power 6, like simply just multiplying the unit. This is going to be the unit. But in this case, this is not going to be the same, because see one thing, here is 1 mole of Mg2 plus, but here is 2 mole of like fluoride. That means here, what will be over here, that is going to get double. Why? Because here the KSP equation is going to be simply Mg2 plus into F minus square. So this, the front end value, coefficient value, it becomes actually the power of the element. So that's what it is going to be. Now, the solubility value of magnesium fluoride is given, which is 1.22 into 10 to the power negative 3. This is the solubility value. That means concentration of MgF2, which is being dissolved, not the actual MgF2. What does solubility mean? That means the portion which is dissolving. Now, if we compare the soluble part with this part, obviously that makes sense. Let me define it in this way. Let's say this is a whole container of, let's say, some substance. But if this much portion is being used, and from there we get the products, let's say these two values, is it logical that we compare this with this whole value? No, because this is the value we got from only this soluble part. That's the same thing. We will be molar ratioing the magnesium and the chloride, sorry, the fluoride, magnesium and the fluoride with the portion which has been dissolved. So this portion has been dissolved. That will be used to find the molar ratio. So if this is the solubility product, doing molar ratio, simple molar ratio, we will find that Mgf2 to Mg2 plus is what? 1 is to 1. So the concentration for Mg2 plus is also the same. But fluoride has twice the mole as Mgf2. That means fluoride will be having 2 times 1.22 into 10 to the power negative 3. Now, placing these values in these places will give us a KSP value. In this case, the KSP value is going to be the product of them, which is 2.98 into 10 to the power negative 14. Now, what about the unit? See, if anything is like, if the initial concentration is what? Mole per dmq for each of them. Now, if mole per dmq is squared, that gives us a value of mole squared dm to the power 6. And here is also another mole per dmq. So that is, sorry, this is minus 6. Multiplying them together, we get mole cube dm to the power negative 9. So that's basically our KSP value. If we do some other examples, we can say, let's say the KSP CuS, which is copper 2 sulfate, given as 6.3 into 10 to the power negative 3. The unit, in this case, non-units are important. So mole per dm to the power 6, moles per dm to the power 6. So they're asking us to calculate the solubility. In the last part, we did KSP value from the solubility. Now we are being asked to find the concentration, solubility. So it's a very simple one. Just write the first equation, the solubility equation, let's say like the reaction. So Cu2 plus S2 minus aqueous, and this is also aqueous. This is solid actually. So we are going to like reverse engineer the process. So we don't know the value for this one, but let's say we know the values for this one. But how do we know the values for this one? Because this is easy to find using the KSP value. KSP value is Cu2 plus and S2 minus, and whatever the mole is, like over here is, and like we can molar ratio them like simply, like whatever the mole is over here, we can molar ratio it with this one. If this is 1:1 molar ratio, we can simply, let's say if this is X, then the more concentration for S2 minus is also X. If let's say there was a 2 over here, then whatever the mole of concentration of copper is going to be, the sulfide is going to have twice the concentration. So that's simple. So if we have X and X, so we can simply place it over here. X into X, that means X squared, and KSP value is 6.3 into 10 to the power negative 3. Finding the X from here, we would get 2.51 into 10 to the power negative, sorry, this is 36. Yeah, sorry, I'm really sorry. This is negative 36. So this is going to be negative 18. And now X is what? X is the concentration for Cu2 plus as well as S2 minus. In solubility, like from solubility part in the previous question, what did we do? We did the molar ratio with MgF2 with the salt. We can simply also do the same molar ratio over here. The salt with the ions, we get what? 1:1 molar ratio. That means the solubility value is also going to be 2.51 into 10 to the power negative 18. Don't forget the concentration value, the unit, which is mole per dm3. Another example could be, let's say, Ag3PO4. The concentration, like the equation will be PO4 3 minus PO4 3 minus aqueous. There's this 3 in front. So they have asked, like they've said the KSP value is given as this 1.25 into 10 to the 1 negative 20, and they're asking us to calculate the value for Ag plus. So they're asking us to calculate the concentration for Ag plus, which is in the saturated solution of Ag3PO4. So obviously, since they have asked us to find the concentration of Ag plus, this is going to be like pretty easy, but there are certain concepts you need to focus here. So writing the KSP equation, what can we say? The front value becomes the power of each of the terms. So that means Ag's value is going to become the front value, the mole value of the equation is going to become its power, which is 3, and PO4 3 minus is simply 8, because since there is only 1 in front of P or no value, so that means we can consider it as 1. This is the actual value. So we have to take an imaginary value, which is there's a variable of x for any of the like compound on any of the ion. We can take it for x, like take for Ag plus as x, but if we do the molar ratio of Ag plus with PO4 minus, that means Ag, whatever mole Ag plus has, PO4 has what, 1/3 of that, because Ag plus has like thrice the amount. So if this is x, if let's say 3, how do I explain? Like, this is 3 times of the mole of PO4 3 minus, isn't it? So that means whatever the mole of PO4 3 minus is going to be, that is going to be divided by 3, because the molar ratio is 3:1. So if we want to make this side what 1, then we need, like, let's do it in this way: Ag plus PO4 3 minus. Now what is the molar ratio? 3:1. This is PO4 3 minus. Now if we want to make the left hand side like 1, so what do we need to do? We need to divide both the side with the left hand side's value. So we are left with 1:1/3. That means if this portion is going to be x, so x into 1, and that portion we also need to multiply with x. So that will be what? X/3. But since this becomes a fraction, we will try to consider the, we'll try to like take the value or concentration for those part which does not have any, let's say, like values in front. Those values which have only 1 in front or no value, we are going to take that as a reference. So if we take this as a reference of x, that means Ag plus will have what now? 3 times of x. So that becomes easier to calculate. So in the KSP equation, we'll be writing it 3x cube times x. Now, placing this KSP value here, we'll be left with 3 3s and 9, x is 27, x to the power 4, because here we have like x cube and here is another x, so multiply each other giving x to the power 4 equals to our 1.25 into 10 to the negative 20, and from here we will get a value of x which is 4.638 into 10 to the negative 6. But that's not the end of the question. Remember, they asked us to further find the value of Ag plus. Now we have found the value of x, which is what, the concentration for PO4 3 minus, but Ag plus is what, price of x. That means 3 times x is going to be what, to should be 1.39 into 10 to the negative 5 mole per dm cube, isn't it? So don't forget to do the calculation, the like further calculation. Let's do a couple of more examples. Let's say in a saturated solution of PbCl2, so it's saturated. It's either saturated. Saturated means like for all like this insoluble salts, they are all in the state of saturated part. So the PbCl2's concentration has been given as let's say 3.5 into 10 to the negative 2. So that's the solubility value actually, mole per dm cube. Now they're asking us to find the value for KSP. Now, if we write the equation PbCl2, Pb2 plus Cl minus, balancing the equation, we get something like this, isn't it? Now, the concentration or the solubility value of PbCl2 is given as 3.5 into 10 to the negative 2. Doing molar ratio, we get what? The Pb's concentration here should be 1:1, so that means Pb2 plus is going to be the same as PbCl2, which is 3.5 into 10 to the power negative 2. For Cl minus, that's going to be twice the amount, isn't it? Why? Because molar ratio is going to be 1:2. So Cl minus is going to be twice as PbCl2's concentration. Using this value in our KSP equation, our KSP equation is going to be what? Okay, it's going to be Pb2 plus, and don't forget the power here, Cl to the Cl minus square. Why? Because there is 2 in front of Cl. And the KSP value should be 1.72 into 10 to the negative 14. I'm just like writing the values over here. Don't like simply write the values without doing the calculation. Do the calculation by yourself. It will help you a lot. These are like actual question paper questions. So I'm doing like some of the examples that you know how what sort of question comes in the like exam. Uh, I'm going to do a few more examples. Let's say 2 to 3 more examples. So let's say another one is given this 25 cm cube of saturated solution of CaOH2. OH2, which requires, let's say, 21 cm cube of 0.05 mole per dm cube of HCl. Okay, so that means this CaOH2 it reacts with HCl. Now, a complete neutralization reaction occurs after that. Why? Because this is a alkali or a base, and this is an acid. So acid and base they react with each other. Complete reaction, complete neutralization reaction, and they're asking us to find the KSP value for our CaOH2. CaOH2, like for this one, for this salt, they are asking us to find the KSP value. Now, obviously, they haven't given us much of information because they haven't given us the concentration of CaOH2 which has been used here. So we need to make sense it from this HCl part. So if we write the equation CaOH2 plus HCl, we get CaCl2 plus H2O, 2H2O, 2HCl. That's the equation, balanced equation. Now the values for HCl is given. We can find the mole from here, which should be around 0.05 into 21 divided by 1000. So this should be our the mole for HCl, and if we do molar ratio, we can get that the HCl is to CaOH is 2:1. So HCl is to CaOH2 is 2:1. So if we want to make the left side 1, so we divide by 2, we'll get 1 is to half. That means whatever the mole of HCl is going to be, the half of that is going to be CaOH2. So that means 0.05 into 21 divided by 1000 is whole divided by 2. That is going to be our concentration, our mole for CaOH2. Now using this mole and this volume, we can find the concentration for what? CaOH2. Concentration is what? Mole divided by volume. So we have mole from here, we have volume from here divided by 1000. We would get our desired concentration, which should be equals to 0.042. I guess, wait, not 0.042. First write the equation, the solubility product COH2, this should be Ca2 plus 2OH minus. So that is actually going to be 0.05 into 21, sorry, 21 divided by 1000 divided by 2, and calculate the concentration divided by 25 into 1000, 0.021. So yeah, 0.021. I would just wrote for the concentration for actually OH minus. So this is actually 0.021. The concentration for this is we are getting 0.021, the solubility value. So if that the solubility value of that is 0.021, so that means the Ca2 plus is going to be 0.021, and for so hydroxide it is going to be what? The twice that amount, because molar ratio is 1:2, that is 0.042. So previously I told the value for actually OH hydroxide, and using this value in the KSP, we would get what? Ca2 plus is going to be itself, but the concentration of OH minus is going to be the the power of 2, because since there is a value of 2 in front. And after doing the calculation, we would get KSP value of 72.7 into 10 to the negative 5. And if you see the mole, there's a like I mean the unit is going to be mole cube 10 to the power -9. Another example could be, let's say, the KSP of an equation of, let's say, PV of an element. I mean the KSP value of an insoluble salt is given as, let's say, 2 into 10 to the power -5, and they are asking us to calculate the Pb2 plus, so the concentration of Pb2 plus in the solution. Now let's write the equation first. PbCl2. Always write the equation, even if like they don't ask or they don't provide you. Try to write the equation. The solubility, like the equation for the solubility KSP, like they're like very easy. So just like simply write the elements and you will be good to go. And it's just like the previous equation, like the one of the previous example. So they are asking us to find the concentration of any of them. We don't know the concentration of this, we just know the KSP value. So we can take any one of them as X, isn't it? We want to take the value which is X, which has this, let's say, the lesser value in front. Which one has the lower value in front? The Pb2 plus, isn't it? So let's take that as X, and that means Cl minus is going to be what? Twice of X, plus we like the molar ratio is 1:2. So the KSP is going to be simply Pb2 plus and Cl minus square. So that means X times X, sorry, 2x square, 2x square, and the KSP value is 5. And solving from here, we get the value of X as 1.71 into 10 to the power -2. Now check if this X is what we assign Pb2 plus as. If it is, then yes. If it wasn't, if let's say we were supposed to find Cl minus, then we would have needed to multiply it with 2, since the concentration was twice the amount. So in this case, this is the concentration. It's mole per dm. Let's do the last example of today, which is, let's say, actually not an example, this is an information to be given, which is by using the KSP value, we can actually like predict if the salt, or let's say if there is going to be any precipitate formed, if there is going to be the formation of PPT. So let's say an example, BaCO3 solid, it undergoes the solubility product concept, CO3 2 minus aqueous. So the KSP equation should be Ba2 plus CO3 2 minus. Now the KSP value is given, let's say, 5.5 into 10 to the power -10 mole square to the power 6. Now if the value, like if we get the value, let's say this product value of the given information, let's say if whatever concentration we are provided with, if we get that product to be, let's say, greater than this 5.5 into 10 to the negative minus the negative -10, then precipitate will be formed. But if the value is less than 5.5, then no precipitate will form. So if this is greater than this value, then PPT will be formed. Otherwise, no PPT formed. PPT formed. So that's an information to be taken. So based on that, let's do our last example, which is, let's say, we have provided you with 1 dm cube of 5 into 10 to the power -5 BaCl2. This is mole per dm cube concentration actually. And over here, we have provided with another 1 dm cube of 10 to the power -4 mole per dm cube of, let's say, Na2CO3, sodium carbonate and barium chloride. Now, if you want to find the mole for BaCl2 from this equation, like from the given information, we can simply do the calculation and we will get the mole is actually 5 into 10 to the power minus 5. Similarly, for Na2CO3, we can find the mole as 10 to the power minus 4 actually. Is it? Yes. Just a minute. Yeah, it is. Why? Because see, don't get confused with the volume in this case. The volume is given as 1 dm cube, which means 1000 cm cube. And we do the calculation as what? Mole equals to concentration into volume. Now, we might want to divide it by 1000, but remember, 1000 is when the volume is given in cm cube. But in this case, the volumes are divided in dm cube. That means we don't need to divide it by 1000. So we simply need to just multiply the concentration with volume. Now, these are the moles we got, and if we, let's say, by the concentration for Ba2 plus in this case, so from BaCl2, in one of the in each BaCl2, how many Ba like how many Ba2 plus are there? One. So that means the molar ratio is 1:1. That means the concentration for Ba2 plus we can find obviously the mole is the same as BaCl2. The concentration is going to be what? Concentration is going to be 5 into 10 to the power minus 5 divided by, now can you say what is the volume? In this case, both the substance have what? Aqueous as a solution, isn't it? Water is added with each other, like 1 dm2 of this solution, which has solvent as water. This also has water as solvent, so 1 plus 1 is what? 2 dm2. So there it is going to be actually 2 dm2. So the total value is going to be 2.5 into 10 to the power negative 5. This is actually concentration for our barium. Now, if we want to find the concentration for carbonate, COC2 minus, we can do it from over here. Each sodium carbonate has how many mole of carbonate? See over here. Each of them has 1 mole of carbonate, isn't it? If it had, let's say, 2 mole of carbonate, what would have been given? When it to CO3, then here we would have written like 2. That means each sodium carbonate has 2 mole of carbonate, but that's not the case. Rather, each of them has 1 mole of carbonate. So COC, this 2 minus is just the ion, the charge of the ion. So that means the molar ratio is going to be 1:1. So that means the mole is going to be same. So from this mole, we can find the concentration in the similar way, 10 to the power minus 4 divided by 2. And since it is already in dm cube, so we don't need to do like the smart multiplication of 1000. This is going to be 0.5 into 10 to the power minus 4, which is actually going to be 5 into 10 to the power minus 5. Now, using these values, both the values, we can actually do the required part which they have asked us to, which is Ba2 plus CO3 2 minus. We already know from the previous part that the KSP for BaCO3 it should be 5.5 into 10 to the power minus 10. Now we need to find the KSP value from the given information which they have provided us with. So KSP is what? Ba2 plus and CO3 2 minus. Combining them, we get a result in this case, which is 1.25 into 10 to the power minus 9. Since this value is what? I mean, this value is less or more. This is less value, lesser value. That means what? That means there is going to be formed. Wait, is there going to be forming ability? So actually, like now remember, like this should be actually less. Why? Let me explain. This should be less because the reason this should be less. Actually, KSP, like what does it represents? This represents the concentration for Ba2 plus and CO2 minus, isn't it? If their product is greater, oh, sorry, no, I was correct. I'm really sorry. Yeah, this should be actually this. So if uh, the value is actually greater than that, this should be in the opposite. This should be in the opposite way. So if if the product is less, if the product of this concentration is less, then what does that mean? That means that less amount of BaCO3 is like dissolved, isn't it? Less amount of BaCO3 dissolved, producing Ba2 plus and CO3 2 minus. So now lesser concentration of Ba2 plus and CO3 2 minus is going to be formed. If less amount of they are formed, that means what? Their product is going to be, the value is going to be less, isn't it? So if the value is less, what does that mean? That means more BaCO3 remains as solid. If more solid is remaining there, that means the solubility is less. That means precipitate will form. But if greater, like the Kc value is greater, that means more concentration of Ba2 plus and CaO3 2 minus. That means the product is going to be a higher value or greater than this value. That means less number or less concentration of BaCO3 is going to be like remaining there, remaining solid. So more will be dissolved. That means precipitate will be not formed. Now over here, what will we find? We find 10 to the power like minus 9. Now 10 to the power minus 9 is greater or 10 to the power minus 10 is greater? 10 to the power minus 9 is actually greater. Why 10 to the power minus 9 is greater? Because in 10 to the power minus 9, after decimal, we have in front almost, yeah, we have 9 zeros in front. But in place of 10 to the power minus 10, we have 10, sorry, in place of minus 9, we have 8 zeros. But in place of 10, we have 9 zeros. That means after 9 zero, there is the like 1 to 5. That means this is a smaller value, isn't it? So if this is a smaller value, that means like if that's a smaller value, that means that is a lower value. But this is a higher value, isn't it? That's a greater value because it has like the like 8 zeros in front and that has a 9 zero in front. Like simply think it in this way: 100 and like 10, which is greater. 100 is greater. So that's basically in that way representing, but in terms of decimal. So since this KSP value is greater than the value over there, KSP greater means more Ba2 plus and CO3 2 minus concentration. So if the concentration of Ba2 plus and CO3 2 minus is greater, that means what? It is insoluble. So no PPT. Okay. So that's basically, if you didn't get it, rewatch it again. You most probably you'll be getting it.